So the title of this lesson is More C of M. What do you think C of M stands for? Yeah. Conservation. Conservation of momentum, what we looked at last day. We said last day that because impulses are equal but opposite, that means that the amount of momentum that you start with on what we called a closed system will equal the amount of momentum that you finish with. I said that lets us analyze collisions and explosions. The amount of momentum you start with will equal the amount of momentum you finish with. We're going to continue that a bit today. But first, we've been talking about crumple zones and how the key to minimizing injury in a car accident is to increase the time of collision. What does increasing the time of collision lower? What does damage in a car accident? Yeah. So it's all about, can I make that smaller? Right? How many of you see those little smart cars, the ones that are really, really tiny driving around? Okay, you know the ones I'm talking about? How much of a crumple zone can you build there? The engineers who designed it, now there's other issues with smart cars. I think they've had some quality control issues, but they're an interesting concept. But when I first saw them, I was like, boy, I don't know if I want to be in a car accident with that. What they've done is the engine is the crumple zone. Yeah.
They also roll in soft.
I haven't checked that out. I haven't looked at their center of mass yet. I would need to double check some verifiable physics-based resources, because I'm always skeptical of almost anything that I see on the internet, as should all of you. This is a video of a smart car. It's going to be guided remotely with remote control into a cement barrier. And it's really pretty good engineering. Let me pause the video. I got to fast forward. It says to 5 minutes, which is right about there. Okay. So you can see we've got a big antenna right there. That's for the remote. This is being piloted remotely. It's going to hit a cement barrier at 70 miles per hour. It's about 120-ish kilometers per hour. So Coquihalla Highway freeway speeds.
James, 10 seconds. 20,
From 70 miles an hour to naught in 1 second.
First thing I know, didn't roll. Okay. What engineers were trying to address two things. Number one, we'd like to minimize injury, but number two, we'd like to make it so that paramedics can get medical attention to the passengers as quickly as possible.
The little smart hit with such energy that it moved 20 tons of concrete, leapt into the air and rebounded to the side of the road. We didn't know what we'd find when we reached the wreckage.
The steel cage has certainly done its job really well. You can still see the original shape, just that one nasty kink there. Don't forget this is a carbon outer roof, the plastic was just shattered. So without even the strength of the roof, there hasn't been that much fit. You can in fact open the door.
That there is pretty impressive. Now let's be clear, if people were in this, you would be pretty severely injured, but would firefighters have to cut you out with the jaws of life, or could paramedics get at you right away? That gets the paramedics to you, what, 10 minutes earlier, 15, 20 minutes earlier? Okay. What about the crumple zone?
Bits fly out. The area you come around the front, you do see...
Hang on, Mr. Dewick. Bring that back.
That massive impact.
So there is the engine as the crumple zone. That's how they designed it, okay? Figured that was going to happen again.
Around the other side, though, it still looks remarkably like a smart car. You can still feel the shape of the door. Indeed, the door not only opens normally, it closes again.
So again, would paramedics be able to get to the passengers? Yeah, very, very quickly. there's trade-offs as always. I'm not saying, oh, a smart car is the safest car to be driving. I am saying that's some really good engineering workarounds to dealing with a problem that is unique to that design of a vehicle. Not much of a crumple zone. Let's talk about toilet paper physics. What? You may have seen in public restrooms where they have the big roll of toilet paper, the huge ones. You may have noticed if you pull the toilet paper slowly, the roll will rotate. What happens if you pull the toilet paper quickly? How can the same thing behave differently in two different situations? How is it that when you yank quickly, the paper rips, but when you yank slowly, you're good? Shouldn't the ripping force be the same no matter what? Well, here's a similar concept. This is from MIT. I'll show you our setup. We have here a block of wood, fairly heavy block. It's tough to see from the back, Cole, but there's a thin black thread right there. There's also another thin black thread right here. This red rope here, it's a safety rope so that if this thread breaks, the block doesn't smash onto the table. But the red rope is not really part of the experiment. What is part of the experiment is the thin rope on top and the thin rope on the bottom. Here's the question. Suppose I want to pull on this thread here and break this thread, not that one. How should I pull? And suppose I want to pull on the bottom thread, but instead I want to break this thread, not this one. How should I pull? Is it possible to decide which thread I want to break? The bottom string, if we pull it quickly, the bottom string breaks. Like the toilet paper ripping when you yank on it quickly. What if we slowly increase the force? Top string breaks. Sort of like the toilet paper roll rotating. How can you explain that? Yeah. You know what? Instead of mass, you might even say a word that starts with letter I. Yeah, okay. Good. Keep going. Oh, it's similar to my tablecloth, magician yanking the tablecloth out. Yeah. My version, which had the container of water. Yeah. The block has enough inertia that if you yank really, really quickly, before the bottom thread can get the block to accelerate really fast, the force is big enough that the bottom thread just breaks. Where if you pull slowly, the top thread, because it's got the block pulling down on it, will break. You may have done something similar. If you've ever seen a stack of magazines and you've wanted the bottom magazine, do you need to remove all the top ones, or what's another way you can get the bottom one? You may have seen, you know what, if I get two hands and if I yank really quickly, I can yank that bottom magazine out. Yes? But what if you pull very, very slowly? The whole stack is going to come with you, or it's going to fall. So we do this all the time. That's not part of today's lesson. That was just nerd trivia physics. Here's the part of today's lesson. So here's where you want to turn your brains on. Okay? We're going to, this is here where it says types of collisions. This is going to be vocabulary we need to know. We're going to break collisions up into two main types. They stick together or they bounce apart. There are a whole bunch of other subtypes that you can do. Not going to worry about that. We're going to say collisions either stick together or bounce apart. The first one, if objects bounce off of each other after the collisions. Curling rocks are a good example, Ella. You won't see a curling rock stick to the curling rock that it hits. Playing pool, billiard balls are another good example. Baseball hitting a baseball bat. You never see the baseball stick to the bat. Some car crashes, not all. A football tackle where you're not wrapping the person up to grab them, but instead you're driving your shoulder through them to bring them down. Or a body check. All of those are examples of where the objects bounce apart, and the fancy physics word for that is elastic. Write that down. The way I remember that is elastic band, rubber bounces apart. That's how I've done it for years. An elastic collision, they bounce apart. Elastic rubber bounces. The second type of collision, Tyler, is where they stick together. When a football player tackles and wraps their arms around the player. Ooh, a dart hitting a dartboard club. That works very, very good. Some car crashes, because some car crashes do stick together. A bullet that enters a target and sticks inside the target without going through the target. Those are called inelastic. And I'm going to start to use those words in questions. I will tell you two cars collide elastically. What I've just told you is afterwards they did not stick together. Or I'll say two vehicles collide inelastically. What I've just told you is they stuck together. Okay? There's a bit of a problem here. If I say we have an elastic collision and I say it really fast, it's tough for your ear to tell, did he say we have an elastic collision or did he say we have inelastic collision? So what I will try and do when I'm speaking is just exaggerate it. I'll often, Josh, say two cars had an elastic collision. I'll put a big pause in there. Or two cars had an inelastic collision. I'll really emphasize it, okay? But you do need to know these two terms, and we'll start using them. Put your pencils down, look up. We're going to finish with this, a little thought puzzle. I'm going to show you several different types of collisions and explosions. Done with lab carts, don't panic. The first type is going to be an explosion. You're going to see two lab carts that are joined together, and what you don't know is there's a spring inside of them. When we press the button, they're going to spring apart. In one situation, Tyler, you're going to make it because you're dipping low. In one situation, both masses are identical. In one situation, one of the masses is bigger than the other mass, and it's your job to try and figure out which one is which. So you ready? Here's the first explosion.
Unequal mass.
Is that same mass, or big mass, small mass? There's the first one, and I'll give you the second one to compare it to.
Equal masses. Explosion.
One of those was big mass, small mass. One of those was same mass, same mass. Let's watch them again.
Unequal mass.
This one here, what do you think? Big mass, small mass, or same mass, same mass? How do you know?
Unequal mass. Explosion.
Don't use the word accelerate. One had a bigger velocity. First of all, before the explosion, what's the momentum? After the explosion, what's the momentum then? 0. If we have a bigger mass, how can it have the same momentum as the smaller one? The bigger mass will be traveling slower velocity, not accelerate, slower velocity. So let's look.
Unequal mass. Explosion.
Okay, which is the heavier mass, the left one or the right one? Left one. Is that okay, Gerard? I've seen a lot of nodding heads. Come on, get up, wake up, or I'll wake you up. Now we're going to see 3 collisions. These are going to be elastic collisions. They won't stick together. We're going to have same mass hitting same mass, big mass hitting small mass hitting big mass. And your job is to see if you can figure out which one is which. Here's the first one for reference.
Elastic, big mass, and small mass.
Second one for reference.
Elastic, small mass hits big mass.
Here's the third one for reference.
Elastic.
Which one of those stood out and looked a little bit different from the other ones? Let's watch the second one again. I think that one was a little weird, wasn't it?
Elastic,
Here's the
small
second
mass
one.
hits big mass.
I don't think those are equal masses. What do you think that one is?
Small mass hits big mass.
Gerard? I don't think it's a big mass hitting a small mass. What?
Elastic,
Convince
small
me.
mass hits big mass.
Because the big ones heavier, so moves less.
But also, the small one transferred pretty much all of its momentum to the big one. If it's a bigger one, what can you tell me about its velocity compared to the small one coming in? I'm looking to see if the box leaves, the second one should leave slower than the first one came in. Yes, it did. That is a small mass passing its momentum to a bigger mass, smaller velocity. Let's look at the first one then. This is either same, or big, small. How do you know? What can you tell me about the velocity of the second object after the collision? Faster, smaller mass, same momentum, faster. Is that okay? And so, in the third one then, if it's same, it should almost be a dead stop, and the second cart should move off at pretty much the same velocity as the first one came in.
Elastic.
Yeah? Pretty close. Pretty close. Okay, we're going to see three more. This is going to be an inelastic collision. They're going to stick together, and it's going to be same mass hitting same mass, big mass hitting and sticking to small mass hitting and sticking to big mass. But I've shuffled the order. See if you can figure out which one is which. Here we go. First one. Inelastic. They're going to stick together. Second one.
Inelastic, small mass hits big mass.
Third one.
Inelastic.
One of those looked a bit different from the other two. Let's watch the second one again. That one stood out in my brain. I don't think this is equal masses. Is this big hitting small or small hitting big? Why?
It's small.
Small mass times velocity, much bigger mass, much smaller velocity, because their mass is now combined. Okay, now let's look at the first one and the third one. So is this first one big hitting small or same hitting same? That one barely slowed. I think it's big hitting small. Let me convince myself by looking at the last one. It should slow more than the one we just saw. Yeah, it did. Okay? So these are the three types of collisions. We can have two types of collisions, elastic or inelastic. Is that all right? Okay. We're going to start to look at word problems tomorrow. We're going to pause here right now. Your homework right now is work on the homework from the last few days.